for mass conservation equation, you have the problem. This is the tricky part. If you're using that equation to approximate this guy, you can this equation. So this is the momentum equation. That is the straight answer, right? So what is the problem here? The problem here is that this equation does not actually preserve their linear momentum. Because when you have two particles and you have the force when you interacting each other, right? If you're thinking J minus I or I minus J, the force from particle J to particle I is different from force from I to J, right? So when you have two particle interaction, you need to make sure that the force acting from each other need to be the same, right? But this equation does not preserve the problem. And therefore, it causing this problem. If you're using this equation, it will causing that sort of problem. So what we did here is, we create a very simple sort of the numerical sample, and we assign a small variation of stress to one particle. We have boundary particle and we have an actual particle here, and we're using the equation to solve for the motion of this particle. So because of the small variation in the stress, it actually produces some vibration. And with this equation, because it does not preserve the linear momentum, eventually you end up with this sort of problem, highly unstable. Okay? So this is the problem of SPS. If we are using this formulation. On the other hand, if you can also actually fix this problem. If you're looking at problem from here, right? This is the big equation does not preserve the linear momentum. But you can fix it by changing the term. So to the left hand side, you have that equation. You have a divergence of stress. I still have divergence of stress here. But then I'm adding another term to the right hand side. This term in principle is 0 because you have a divergence of 1 is 0, right? And then if I'm adding this term and then I'm actually using some standard SPS formulation, I can get the equation. The difference is here. So now the force acting on particle I is actually the sum of the two forces. And when you apply to J, they are the same amount. So this equation preserves both linear and angular momentum. Okay. So if you're using this equation, then you can quite stable results. You're no longer seeing the instability that you have in the previous equation. So this is the tricky part of SPS. You need to understand how the SPS works, right? and to make sure that you know exactly what numbers you should use. So that is the momentum conservation equation. So then now it's come to the conclusion of this part. So basically we're talking about mass conservation equation. We have three different ways to approximate the mass conservation equation. The first one is obviously inaccurate. The second one was the one derived from the fundamental physics, where we taking time derivative of the density summation. And the third one was the standard one. So you're looking at the second and the third one, they're slightly different. In this term. So M tray here is the mass. So mass equal to rho times V. The bottom equation we have V, rho is rho I. In this equation we have rho J. So what happened here is, for that equation, the approximation is depending on the neighboring mass. Right? This approximation depending on the mass of neighboring particle. Meaning what? If you have a particle with significantly different mass, this equation would cause some problem. And therefore this equation is only suitable for homogeneous problem. But for this equation, it doesn't depend on the mass of particle J, but depending on the volume of particle J, it's more or less similar. We have density different, the volume is still more or less similar. So this equation is suitable for the multi-layer when the thickness storage layer. This is again some sort of trick part that we need to make sure we select a suitable way equation. Momentum equation. This equation does not conserve the momentum. Angular and linear momentum is not highly recommended. But you can use these two equations. Okay? That two equations is under the form can be used. Alright, what else? So far we're talking about the SPS approximation. We have SPS approximation for function, for gradient, And how we using the SPH approximation for the mass and molecular concentration of equation, and what is the drawback, what is the traps when you're looking to the SPH. We have not actually discussed about the kernel function. What is the kernel function? So this is an example of several kernel functions. This is the property I have discussed earlier. A kernel function need to satisfy these conditions, right? Need to be some of the conditions here, symmetry supposed to define, practice support, and to ensure that the approximation preserves mass. Here you have three very popular kernel functions that's commonly used in here. You have Gaussian, cubic, and one kernel function. Okay? And this is the first grade. Now, when it comes to the kernel function, there's another confusion. Right? And then this is another source of the criticism. At the moment, in the literature, especially looking at some paper in the last few decades, people are talking about SPH having problem of tensile instability. Where it comes from? So, in our research, we're looking at, I'm going to show you that sort of tensile instability was actually coming from the misuse of kernel function. Okay? I'm going to show you here also. This is an example of cubic SPH function. And in this example here, this phase on delta x is referring to the sign of this domain. So when you're moving to the left-hand side, the sign increase, which means you force the approximation at the same location, but if you're moving to the left-hand side, you force the kernel function to take more particles, right, compared to the left-hand side. You can see that with the cubic SPH function, when you have a supporting domain that reasonably compact, you're getting pretty good solution. But as you increase moving to the left, especially when you're actually having a large number of particles within the supporting domain, you obtain this problem. And this problem is referred to as tensile instability. But the correct word should be pairing instability. You can see the particles actually pairing. So this is the center of the issue of SPH when you're not using the correct kernel function. So where is the source of kernel function? Now where is the source of the error? If you're looking at this line here, this is the governing equation, this is the molecular equation.